name is Michael Pendazis, and this is Math 241 Probability and Statistics, online lesson number 4. Thanks for tuning in. So let's first go over what we did last lesson. And so last lesson, we talked about random phenomena with Poisson distributions. We talked about the Poisson process. We talked about lambda. We talked about the cumulative distribution function of discrete random variables. We found the cumulative discrete function. So that was the end of chapter 4. And then we started chapter 5 last class. We talked about continuous random variables and probability density functions. We talked about what a continuous random variable is. And we talked about the probability that our x was between A and B, and that x was at most little x. Okay? And so we talked about that. Okay, so we did all of that last class. And so this class we're going to continue with chapter 5. And so we're going to just keep going with chapter 5. Let's talk about 5.3 on continuous random variables. Okay. And so definition 5.1. A real value function capital X defined on a sample space S with probability set function capital P is a continuous random variable provided there is an integrable function little f such that the probability that x is at most little x is equal to the integral from negative infinity to little x of f of t dt. And that's for any real number x, which we can say by writing these two inequalities. Okay? So the function little f here, that function there, is a probability density function. Of the random variable x. Okay? So a real valued function capital X defined on a sample space S with probability set function capital P is a continuous random variable provided that there is an integral function little f such that this equation holds. Such that the probability of x being at most little x is that integral from negative infinity to little x of f of t dt for any real number little x. Okay? And this little f is the probability density function of a random variable capital X. Okay, so we have that definition of a continuous random variable. Okay, so let's keep going. And so 5.4 is finding probabilities for continuous random variables. Okay? And so these are the rules for finding probabilities for continuous random variables. Okay? So the rules for finding probabilities for continuous random variables. One, the first rule is that the probability that x is some fixed number, little x, is 0 for any real number x. Again, those two inequalities mean that our little x is any real number. Two, the second rule is that the probability that x is strictly less than some fixed x equal to the probability that x is less or equal to little x, which is equal to the integral from negative infinity to x of little f of t dt. And this is still for any real number x. Three, the third rule, is that the probability that a is less than or equal to x less than or equal to b is equal to the probability that a is less than or equal to x strictly less than b, which is equal to the probability that a is less than x less than b, which is equal to the probability that a is less than x less than or equal to b. And that's equal to the integral from a to b of little f of t dt, and this is for a strictly less than b. Okay, and so that means is that you can put less than sign or less than or equal to sign either one of these, and the probability is the same. All right, and that's because the probability of x being a specific value is 0. And this is for a continuous random variable, right? In discrete random variables, we could say that there is some positive probability of our variable being a specific number. That was for discrete random variables. Here is a continuous random variable, and for continuous random variables, your variable cannot, you assume that there's virtually no way, we say the probability is 0, that your variable is going to equal some fixed number, okay? And so we have those three rules. And so these are three rules we have for probabilities of continuous random variables. Okay. Let's keep going. So we have those three rules in mind the entire time. Okay, and I'll mention them again a little bit when they come up. Okay, so let's observe that the probability of a strictly less than x less than or equal to b is equal to the probability that x is at most b less than or equal to b minus the probability that x is at most a. Okay? And this is equal to the integral from negative infinity to b of little f of t dt. And subtracting integral from negative infinity to a, little f of t dt. And so there's an integral rule in calculus where if you take the integral from a to c, the integral from a to b plus the integral from b to c is equal to the integral from a to c. And so we're applying that rule here, except now we're saying that we're saying the integral from a to c minus the integral from b to c is equal to the integral from a to b. But now our so we have that rule there, and what we want to say is that the integral from negative infinity to a plus the integral from a to b is equal to the integral from negative infinity to b. And so that's how we're using that rule. Okay? Okay, so now this is equal to the integral from a to b of f of t dt. Okay, let's also observe that if you take the limit as c approaches infinity of the integral from x minus c to x of f of t dt, then the limit as x approaches 0 of the probability of x minus c is strictly less than x less than or equal to, well, x, here this is capital X. Okay. And so if we take the limit of that, then that's going to equal the limit, when c approaches 0, of the integral from x minus c to x of f of t dt. And so what that is equal to is the integral from x to x of f of t dt, and that's equal to 0 by integral rules, right? If you take the integral from something to itself of any function, it's 0, right? And so that implies that the probability of x equaling little x here, the only way this integral can work as c approaches 0, if capital X is little x. And so this is the probability that x is equal to that little x. That probability is 0. And so that taking this limit and finding that it's 0 is proving that the probability of x being any fixed number is 0. Okay? And so that was one of the 3 rules that I mentioned before. So simple. Now let's look at example 5.2. Okay, so I'm going to let x be a continuous random variable. So continuous random variable with probability density function. That's probability density function. Little f of x is equal to 2x for 0 less than x less than 1, and 0 elsewhere. Okay, so we have a probability density function here, and we have a continuous random variable. And so what we want to do is find the probability that x is at most 0.4. Okay, well that's just the integral from negative infinity to 0.4 of little f of t dt by the definition of our cumulative distribution function. And so then that's equal to, well now that's equal to the integral from negative infinity to 0.4 of 2 t dt. So I'm just using t here as a dummy variable, okay? And now since it's only defined from 0, f is only non-zero from 0 to 1, this is the integral from 0 to 0.4 of 2 t dt. And so the antiderivative, an antiderivative of 2t is t squared, evaluated from 0 to 0.4. That's 0.4 squared minus 0 squared. And so that's 0.16. Okay? So the probability that x is at most 0.4 is 0.16 in the problem, right? And x is a continuous random variable, and f is our probability density function. Okay? The probability that x is greater than 0.2 is equal to 1 minus the probability that x is less than or equal to 0.2. And so that's 1 minus the integral from negative infinity to 0.2 of little f of t dt. And that's equal to 1 minus the integral from 0 to 0.2 of our function 2t dt. And it's equal to 1 minus an antiderivative 2t is t squared, evaluated from 0 to 0.2, and that's 1 minus 0.2 squared minus 0 squared, and that's equal to 1 minus 0.4, and that's equal to 0.6. Oh, sorry, this is 0.04. 0.2 squared is 0.04. And so 1 minus 0.04 is 0.96. Okay. So those are 2 of the problems. Another problem is, let's say, what is the probability of 0.2 less than x less than 0.4? Well, that's equal to the probability of x is less than or equal to 0.4 minus the probability that x is equal to 4 minus the probability that x is less than or equal to 0.2. Okay? So saying x is strictly between 0.2 and 0.4 means it's less or equal to 0.4, it's not 4, and it's not less or equal to 0.2. And so this is equal to the integral from negative infinity to 0.4 of 2t dt minus 0, because the probability of x being any particular number is 0, minus the integral from negative infinity to 0.2 of 2t dt. And so that's equal to the integral from 0.2 to 0.4 of 2t dt, and that's equal to t squared evaluated from 0.2 to 0.4. That's 0.4 squared minus 0.2 squared. And so that's 0.16 minus 0.04, that's 0.12. If you evaluate that, that's 0.12. Okay. Okay, so those are a few more problems. Now another problem is, what is the probability of x equaling 0.5? So the probability x, again, is any particular number is 0, so that's 0. And the probability that x is less than 0.4 is equal to, well, you could also think of it as the probability from 0 to 0.4 of 2t. To be very technical, which I like to be, this is the probability x is less or equal to 0.4 minus the probability of x equaling 4. But now it's because x can't be negative, right? This is obviously the integral from 0 to 0.4 of 2t dt, and that's minus 0, right? This is 0. And so now this is t squared, evaluated from 0 to 0.4. And so that's 0.16. Okay. And so in example 5.2, you find a few probabilities with a continuous random variable and with a probability density function. Okay, so example 5.3. Okay, so suppose in a region, daily rainfall inches is a continuous random variable x with probability density function f of x defined by little f of x is equal to 3/4 times 2x minus x squared, and this is for 0 less than x less than 2, and then it's 0 elsewhere. Okay, so we have a continuous random variable x, and we have a probability density function f of x. Okay, so the two important points to make sure it makes sense, right? We have a continuous random variable x, and we have a probability density function, little f of x, defined that way. And so we're going to find a few things. And so for part A, we're going to, what is the probability that rain falls at most 1 inch? Okay, we want to find the probability that rain falls at most 1 inch. So the rainfall in inches, how much it is capital X. Okay, so x is the amount of rainfall in inches. And so saying rainfall is at most 1 inch, that's saying x is less than or equal to 1. X is measured in inches. Okay, so we found the probability x is less than or equal to 1. And so because we have our probability density function little f of x here, we can say that this is the integral from negative infinity to 1 of f of x. I'm going to use f of x here. And now to make things easier on ourselves, this is only non-zero from 0 to 2. And so I can get rid of the negative part here. And I can say this is from integral from 0 to 1 of f of x, which is defined over there on 0 to 1. Okay, and when you compute this integral, definite integral, you find that probability. Okay? And so computing that integral, you get that's equal to 0.5. Okay, so you have to be able to compute an integral. So here, I had an integral and I computed it, and so, okay. So if you have questions about that, you can ask me. You compute definite integral, it's 0.5. Okay, and so the goal here is to find that the probability we're looking for is equal to a definite integral, and then compute. Okay, so that's part A. Okay. So for part B, we want to find the probability that the rainfall is greater than 1.5 inches. Okay? So the amount of rainfall in inches, that's x. And so this is the probability that x, the amount of rainfall in inches, is greater than 1.5. And so because we're only dealing with non-zero values from 0 to 2, this is the same as the integral from 1.5 to 2. And we don't have to worry about x equaling 1.5 because the probability of x equaling 1.5 is 0. Okay, so we're going to go from 1.5 to 2 of f of x, which is 3/4 2x minus x squared dx. And when you compute this definite integral, that's the answer, that's the probability. And so that integral is equal to 0.15625. And so now that's the answer to part B. Okay? You want to convert your probability to a definite integral, and you calculate it, and that's your answer. Okay? That's part B. Part C. Part C, the probability that rainfall is between 0.5 and 1.5 inches. Okay, that's the probability that 0.5 is strictly less than x, strictly less than 1.5. Right? X is the amount of rainfall in inches, and so saying it's between 0.5 and 1.5 means we get these two inequalities. Okay, and so that's equal to the integral from 0.5 to 1.5 of f of x. And so now we have that our answer is the value of this definite integral, and that's equal to 0.6875. Okay, and so you can use the fundamental theorem of calculus to calculate that definite integral. Find an antiderivative of the integrand, evaluate it at the upper limit of integration, and subtract its value at the lower limit of integration. Okay, and so part D. Part D is what is the probability that rainfall is exactly 1 inch? Okay, sounds like a difficult question, but it's very easy. It's probably that our continuous random variable is equal to some fixed number, right? It's not a range of values. We just want to know what the probability of a continuous random variable equaling this number 1 is, and that probability is 0. A continuous random variable, we say the probability of it being any fixed number is 0. So D is very easy. Okay, so that's part D. Then part E, so part E, the probability of the rainfall is less than 1 inch. So that's equal to the probability that x is strictly less than 1. X is the range of amount of rainfall in inches, and we want the value of x to be less than 1. And so probability that x is less than 1 is equal to the probability that x is less or equal to 1 minus the probability that x is equal to 1. And so that's equal to the probability that x is less or equal to 1 minus 0. And what that's equal to is we found in part A, we found that the probability that x is less or equal to 1 this is equal to the probability that x is less or equal to 1, and that's equal to, by part A, 0.5. Okay, so we already found this, and we found this 0.5. And so in part E, we don't even have to calculate a definite integral. We can just refer to a probability we found earlier. Okay, and so that's part E. So those are the 5 parts of this example. Okay, so let's keep going. So in example 5.5, we show that there must be a third type of random variable. Okay, and so this is an example of a situation that you cannot describe as being a continuous random variable nor a discrete random variable. Okay, so we're going to have to disprove that in this situation that it could be either. So we toss a coin, and if it heads, the player drinks 10 ounces of beer. And then if tails, the player randomly drinks an amount randomly drinks anywhere between 0 and 10 ounces of beer. Okay, so a player tosses a coin. If it's heads, he or she drinks 10 ounces of beer. If it's tails, the player drinks any random amount between 0 and 10 ounces of beer. Okay? And so the goal here is to show that this experiment, in this experiment, x is not discrete nor continuous as a random variable. Okay? So it's not discrete nor continuous. Okay? So to show it's not discrete, right? To show it's not discrete, well, the set of possible, and so actually, when we point x is the number of ounces of beer drunk by the player. Okay? So the set of possible values of x is not discrete. Okay? Right? It's actually the set of possible values of x is anywhere between 0 and 10, but all the real numbers in that interval. And so it's not a discrete amount. It's not a finite amount, and it's not a countably infinite amount of values, okay? So something that you could think of as looking kind of like the real line is not a discrete amount, okay? The real numbers are not discrete. It's not a discrete amount of things, okay? So the set of possible values of x is not discrete, and so because the sample space, because the set of possible values of x is not discrete, sorry, not the sample size. I mean, the set of possible values of x is not discrete, and so it's not a discrete random variable. Now, it's not continuous also. And here's why it's not continuous. If you want to know the probability that x is equal to 10, right? If you want to know the probability that this player drinks exactly 10 ounces of beer, it's at least half. Because when you flip heads, you drink 10 ounces of beer. That's 50% chance you're going to drink exactly 10 ounces of beer. And so we don't know if it's equal to 50%, but we know that the probability is at least 1/2. Because if you flip heads, you drink exactly 10 ounces. That's 50%. And then somewhere in tails there's some chance you might drink 10, right? Some positive amount. And so you're only adding to 50% with the tails possibility. So that means that the probability that you drink exactly 10 is greater or equal to 1/2. And that means that it's not equal to 0. That means that the probability that x is equal to exactly 10 is not equal to 0. And we said that one of the rules for a continuous random variable is that the probability that it equals some fixed number has to be 0. And so this contradicts the rules that I stated earlier. And so that means that we do not have a continuous random variable. And so this is an experiment where we see that our random variable is neither discrete nor continuous. And so that points to the existence of some third type of random variable. One that could describe this situation, one that's not either of these two. Okay? Okay. Okay, and so that's the end of 5.4. And so now the homework for this section is pages 150 to 152, and this exercise is numbers 1, 2, and 4. Okay, and so that's the homework for 5.4. Okay. Okay, so this is also posted online. So let's keep going, and let's move to 5.5. And so this is on cumulative distribution functions. Continuous random variables. Okay, so cumulative distribution functions of continuous random variables. And so first let's define it. So definition 5.2, let capital X be a continuous random variable. That means continuous random variable with probability density function little f, probability density function. The function capital F of x is equals the probability of x is at most less than or equal to x is equals the integral from negative infinity to little x of f of t dt, where negative infinity is less than little x less than infinity, where x is a real number. And this is the cumulative distribution function. And we're going to use the abbreviation CDF for cumulative distribution function. Okay, so the cumulative distribution function, abbreviate with CDF. Okay, so that's our definition. Okay, so now let's look at an example. Example 5.6. Suppose the temperature of a fluid is never less than 50 degrees Fahrenheit, nor more than 51 degrees Fahrenheit. Also, if capital X is the temperature of the fluid above 50 degrees Fahrenheit, the CDF, the cumulative distribution function of capital X, is given by capital F of X, which is equal to 0. X is negative. It's equal to X for 0 less equal to X is equal to 1, and 1 if X is greater than 1. Okay, so we're given the CDF, the cumulative distribution function of our continuous random variable capital X, and we're going to find a few things. We want to find the probability that X is less or equal to negative 1. Well, that's equal to capital F of negative 1, right? That's what the cumulative distribution function says, that capital F, the cumulative distribution function of some number, is the probability that your random variable X, your continuous random variable X, is at most that. And so we know capital F of negative 1 is 0. Okay. And now the probability that X is less or equal to 0.5, well, that's capital F of 0.5. And 0.5 is in this interval, and it says that capital F of one of these X values is itself. So this is equal to 0.5. The probability that 0.2 is less than X less than 0.5, well, that's equal to 1. Oops. That's the probability that X is less than or equal to 0.5 minus the probability that X is equal to 0.5 minus the probability that X is less than or equal to 0.2. Okay? So if X is strictly between 0.2 and 0.5, that means X is less or equal to 0.5, and that it's not equal to 0.5, and that it's not less or equal to 0.2. And so that this is equal to capital F of 0.5 minus 0, because the probability that X is some fixed number for continuous random variable is 0, minus capital F of 0.2. Right? This you can find using capital F, and this you can find using capital F because it's less or equal to some number. Okay, and so capital F of 0.5 is 0.5 minus capital F of 0.2, which is 0.2, and so 0.5 minus 0.2 is 0.3. And that's the answer. Okay. And so now, for example, 5.7, let capital X be a continuous random variable with probability density function little f of x is equal to 1 for 0 less than x less than 1 and 0 elsewhere. Find the CDF of capital X and sketch the graph. Sketch the graph of capital F of X. Okay. Okay, so we want to find the CDF, and so the first part, well, let's assume X is less than 0. Then capital F of x is equal to the depth interval from negative infinity to little x of f of t dt. And so now f, when x is negative, is 0. This is the integral from negative infinity to x of 0 dt, which is 0. So that's for x is negative. The second thing is that if 0 is less than equal to x, less than equal to 1. Okay? Then capital F of x is equal to the integral from negative infinity to x of f of t dt, and that's equal to, and so that's equal to now 1. Well, f is 1, so this function is 1. It's the integral from 0 to 1 of, sorry, yeah. 0 to 1, 0 to x of 1 dt. The function's 1, but x is here, okay? And so, okay, and so now this is just, now this is just t value from 0 to x, which is x. So capital F of x is equal to x there. That's if x is in these range of values. And 3, if x is greater than 1, then capital F of x is equal to integral from negative infinity to x of f of t dt. And now, this is now going, since x is greater than 1, we know it includes this entire integral here. And so we go from 0 to 1, and it's 1 there and 0 everywhere else. And so now this is equal to 1. Okay? And so we've now found, for every possible value of x, we've found the value of capital F of x. And so our conclusion is that our capital F of x is equal to 0, and that's if x is negative, it's equal to x. If 0 is less than x less than equal to 1, and it's equal to 1 if x is greater than 1. And so that's capital F of x. Okay, and so we now found capital F of x. Okay. Okay. Now, and then the graph of this capital F of x that we just defined is capital F of x, that's 0, that's 1, this is 1, if, and some reminder of what I just read before, capital F of x is 0, if x is less than 0, little x, if 0 is less than or equal to x less than or equal to 1, and 1 if x is greater than 1. Right, that's our capital F of x. And so you graph it, it's 0 for x less than 0. It's 1 for x greater than 0. So those are constant values right there. Those are lines. Just shading them in. And then it's the graph y equals x, where y is capital F of x, from 0 to x to 1. It includes the endpoints. So it's going to be 0 here, it's going to be 1 here, and then just that line segment there. And so this is the graph of y equals capital F of x. This is the graph of the cumulative distribution function for this continuous random variable. Okay, and in the book, this is figure 5.4. Okay, and so that's the end of section 5.5. And this is the homework on page 154, exercises numbers 2 and 4. Okay. Okay. So that's that. And so now let's talk about 5.6. And 5.6 is on properties of probability density and cumulative distribution functions. Okay, so we're going to talk about probability density and cumulative distribution functions. And so we're going to let capital X be a continuous random variable with probability density function little f of x and cumulative distribution function CDF capital F of x. Okay, and so the following are consequences of our definitions. Okay, our definitions 5.1 and 5.2. Okay. Right, the definitions of the cumulative distribution function and our continuous random variable. Okay, so our definitions of x and capital F of x. So definitions of capital X and capital F of capital X. That's 5.1 and 5.2 of a continuous random variable and a cumulative distribution function on that continuous random variable. Okay, so as consequences of those two definitions, you have the following. You have the integral of f from negative infinity to infinity of little f of x dx is equal to 1. And that f of x is greater or equal to 0 at all points where f is continuous. 2. The limit as x approaches negative infinity, capital F of x, is equal to 0. Okay, and the limit as x approaches infinity, capital F of x, is equal to 1. And capital F of A is less than or equal to capital F of B for A less than B. Okay? So the cumulative distribution function says what's the probability of capital X is at most some fixed x. Well, if the fixed x you're thinking of is going to negative infinity, then saying that the probability that capital X is at most this thing going to negative infinity is 0. And if your fixed x is going to positive infinity, then the probability of your capital X being at most something that's tending to positive infinity is 1. Okay? And your capital F is an increasing function. As your input increases, the cumulative distribution function increases. Okay, in value. Okay. 3. The third thing, capital F of x is continuous at all points x where capital F, where little f of x is continuous. Okay, so capital F of x is continuous at all points little x where little f of x is continuous. Okay, and sorry. Capital F of x is continuous at all points x where negative infinity is equal to less than x, less than infinity. For d capital F of x dx exists, it's continuous at all points where little f is continuous. 5, little f of x is equal to d capital F of x dx, where, at all points where d capital F of x dx and exists, and little f is continuous. By the where I mean it, values of x, where d capital F dx exists and little f is continuous. And 6, the probability density function of a continuous random variable need not be unique. Okay? Okay, and so we have these 6 consequences of the definition of a continuous random variable and a definition of a cumulative distribution function. Okay, so we have these 6 statements here that we say are true. Okay. This would be 6 things we can deduce from those 2 definitions. Property 1 can be a definition of a probability density function in PDF. Okay. Remember, property 1 is the integral from negative infinity to infinity of f of x dx is equal to 1, and f of x is going to equal to 0. Where f is continuous. And so this can be a definition of a probability density function. We'll just have this. Okay. And now property 6 means we should write a probability density function of capital X because it's not unique. So word A there, okay? So when we talk about probability density functions, we're going to say a probability density function because it's not unique. Okay, property 6 says it doesn't have to be unique. So these 2 things to note. Okay, and so let's do one more example. So one more example, for example 5.8. So let capital X be a continuous random variable with cumulative distribution function, CDF, given by capital F of X is equal to 0 for x less or equal to 0, 1/4 x to the 4th, x squared is less than x less than 2, and then 1 for x greater equal to 2. And we want to find the probability density function, find the PDF of our continuous random variable x. Okay. Okay, and so the solution is that by property 5, which I'll say what that is, we get, well, what it says is that little f of x is equal to d capital F of x dx. That's one of the things it says. And that's equal to, if you take the derivative, you take the derivative of this thing, and the derivative of 1/4 x squared is 1/2 x. And that's if for 0 less than x less than 2. Okay? And then if you take the derivative of a constant at 0, so derivative of 1 is 0 and derivative of 0 is 0, and that's for all the other values of x. And so it's 0 elsewhere. Okay? And so now we're just about done. And now I'm going, so now here's the homework, pages 155 to 157, exercises number 7 and 10. Okay? And so this is for section 5.6. Okay, so we finished 5.6, and that's the homework for it. Okay? And so we'll stop there, and I'll see you next time.